Hey class, welcome to this lesson on metallic bonding and a comparison of the bond types, ionic, covalent, and metallic. For this lesson, you're going to need a handout provided by your teacher. It's two-sided. It's got the metallic bonding notes on one side, and on the back side is a compare and contrast chart for the rest of the notes. Let's start out with what is a metallic bond. Metal atoms can release their valence electrons into what is known as a sea or pool of valence electrons. The bond that results from this shared pool of electrons is called a metallic bond. The unique properties of metals can be explained by the sea or pool of valence electrons. Metals have great shapeability, the ability to be malleable and ductile. Let's look at this graphic from the Chemistry Connections textbook, an atomic view of metallic bonding. Each atom in this model has a group 2 metal releasing its valence electrons into a pool of electrons to be shared by all of the metal atoms. Group 2 metals could be magnesium or calcium. All of the elements in that family always want to lose 2 electrons. So you can see the +2 cations have arranged themselves in a crystalline structure, very similar to an ionic substance. The difference is that the bonding in metals is not rigid. As a metal is struck by a hammer, the atoms slide through the electron sea to new positions while continuing to maintain their connections to each other. The electrons are mobile. We say they're delocalized. They're free to move about within the sea or pool of valence electrons. The same ability to reorganize explains why metals can be pulled into long, thin wires, what we call ductility. Metals also have great conductivity. Because the valence electrons of all the metal atoms are not attached to any one metal atom, they can move through the metal when an external force, such as that provided by a battery, is applied. Electrical current is the flow of electrons through the metal. Well, to have electrons flowing, you need free mobile electrons, and those are available in the pool of valence electrons. Finally, the luster or shine of metals can also be explained by the electron sea or pool concept. The mobile electrons in metals have a wide range of energies and can absorb and re-emit light over a wide range of wavelengths. This ability gives metals their characteristic shine. As you've probably realized, the answer to the question, why are metals shapeable, why are they good conductors, and why are they lustrous, why do they shine, is always the same. These properties are due to the pool of valence electrons, the mobile, free electrons that can move about and be shared among all of the metal atoms in the substance. Next, we're going to compare ionic, covalent, and metallic. The first column summarizes properties of ionic crystals, formerly units that we've talked about in Chapter 7 that have ionic bonds. The second column emphasizes the properties of molecules. These are substances that we talked about in Chapter 6 that had covalent bonding. And the last column discusses metals, the metallic bonded items that were just discussed in this lesson. Ionic crystals have localized electrons. The electrons are held in place in the crystalline structure. Molecules also have localized electrons. Pairs of electrons are shared between atoms and held in place within the molecule. It's only metals that have delocalized electrons, free mobile electrons that can move and reorganize within the pool of valence electrons. Ionic crystals are generally crystalline solids at room temperature. Molecules can be solids, liquids, or gases at room temperature. This is due to the difference in intermolecular forces and whether the molecules are polar or nonpolar. Metals are solids at room temperature, with some exceptions, notably mercury, a liquid metal. Ionic crystals are considered to be electrolytes. These are substances that when dissolved in water or in the molten state can conduct electricity. Molecules are non-electrolytes. They do not conduct electricity when dissolved in water or molten. Metals are not classified as electrolytes or non-electrolytes. They are simply classified as conductors of heat and electricity. We will be doing a lab on electrolytes and non-electrolytes, so make sure you've jotted down the definitions for those terms here in your notes. Ionic crystals are considered to have strong interparticle forces. Comparatively, molecules have weak interparticle forces. This means that adhesive properties like melting point and boiling point will be affected by the interparticle forces. Ionic crystals would have higher melting and boiling points due to their strong interparticle forces, whereas molecules would be considered to have relatively lower melting and boiling points. Ionic crystals dissolve easily in water. Molecules are less soluble in water. Solubility is related to dissolving ability. Certain substances, molecules like sugar, can dissolve very easily in water. Other molecules, especially if they're nonpolar, have a more difficult time dissolving into water. Ionic crystals are considered to be rigid and metals are considered to be malleable and ductile. This is easily explained due to the difference in the electrons for these types of crystalline structures. Ionic crystals have localized electrons, electrons that are held in place within the ionic crystal, whereas the metals have delocalized mobile electrons that are free to move about and reorganize.